Welcome back. We are in Chapter 5 now. So Chapter 5 has two sections. I've kind of just lumped them together into one short presentation here. Chapter 5 is really just giving us a little introduction to everything we're going to see in Chapters 6 and so on. So I'm not going to spend too much time working on it here because we'll get to work with it in context and see what this all means way more in the later chapters. So this is just a short presentation introducing some ideas to us. It's going to be a little wordy, so sorry in advance for that. First, remember that in Chapter 3 we introduced this idea of a sampling distribution. So the sampling distribution is what you get if you find the distribution of every possible sample, of the sample statistics that could be computed for every possible sample of the same size from the same population. Right, so if we took every possible sample of a size 5 from some population and calculated the mean, we would get the sampling distribution of X bar from that. But that's not possible, right? You can't take every possible sample, and even if you could, it would take you forever, so that's not what we do. We typically just take one sample and do our best to estimate the sampling distribution, to approximate it. We've already seen ways to approximate the sampling distribution computationally, for example, bootstrapping and randomization tests. Now we're going to look at a theoretical way to do it. So if you've taken AP Stats or some other stats class, this is where things are going to start looking familiar to you. You might have noticed that many sampling, bootstrap, and randomization distributions have the same shape. They're symmetric and bell-shaped. What else have we talked about recently that's symmetric and bell-shaped? Right, the normal distribution. So it turns out the normal distribution can help us approximate the sampling distribution theoretically, assuming some conditions are met. So what allows us to do that is the central limit theorem. So this is, we mentioned that the normal distribution was arguably one of the most important distributions in statistics. The central limit theorem is arguably one of the most important theorems in statistics. So basic idea is this: for random samples with a sufficiently large sample size, the distribution of many common sample statistics can be approximated with a normal distribution. So as n goes to infinity, things are going to look more and more normal. So what is sufficiently large? Well, for now, I'm not going to answer that. Sufficiently large depends on your situation, depends on what statistic and parameter you're using. So we'll talk about that in each context starting in Chapter 6. So right now this is just the general idea of the central limit theorem, but we'll talk about specific cases of it. And often we don't say central limit theorem, we say CLT, so we abbreviate it. And this can help us in hypothesis testing. So the normal distribution that best approximates a bell-shaped randomization distribution has a mean equal to the null value of the parameter and standard deviation equal to the standard error. That is, the distribution we're dealing with would be n, null parameter, comma, standard error. And remember, the null parameter, that's the number that you're writing in your hypotheses. And the standard error, well, we can find that. When the randomization distribution is shaped like a normal distribution, a p-value can be found as the proportion of this normal distribution beyond the observed sample statistic in the direction of the alternative, or twice the smaller tail for two-tailed tests. That sounds perhaps kind of confusing, but we did this with the randomization tests, right? We looked at what's the probability of seeing what we saw or something more extreme. Same thing here. It's just instead of a randomization distribution, we now have a normal. And when the distribution of the test statistic under the null is normal, we compute a standardized test statistic like so. It's a z, because it's normal, and it's standardized, so standard normal is the normal 0-1 distribution, or the z. So it's sample statistic minus null parameter, so sample statistic is what you observed, null parameter is the number you wrote in your hypotheses, divided by standard error, and we'll see how to calculate standard errors later. It can also help us in confidence intervals. So in chapter 3, if we wanted to find a confidence interval, specifically say we want a 95% confidence interval, we look for an interval that contains 95% of the bootstrap samples. Similar thing, we want to find an interval that captures the middle 95% of the area under our normal curve. If a bootstrap distribution is bell-shaped, then a p% confidence interval can be found as the interval containing the middle p% of the normal distribution with a mean equal to the observed sample statistic and standard deviation equal to the standard error of that statistic. So last time our mean was the null parameter, or the null value of the parameter, whatever they called it. This time your mean is your observed statistic. In a hypothesis testing situation, you assume the null is true until proven otherwise, so that gives us this null value. Here, we haven't, in a confidence interval, we have not made any such assumption, so you don't have a null value, you've just got what you saw, so your best guess here to center your distribution at is your observed sample statistic. And if the distribution for a statistic follows the shape of the normal distribution with standard error, SE, then we can find a confidence interval using this formula. Take your sample statistic plus or minus z times your standard error. Similar to what we were doing before, right? But we didn't have a z there, we had a 2 or something like that. So now it's going to be our z value. And that brings us to the end here of chapter 5. Like I said, this was just a very brief introduction to the ideas that we're going to see over and over and over again in slightly different contexts for the next few chapters. So that was kind of short, kind of fast, but promise we'll look at all of this in way more detail in the next few sections. So no homework from this section. I don't think that would be helpful, so we'll save all the homework about this stuff for the next few chapters.